All right, continuing on to chapter 31, we're going to talk about resistors in parallel and then groups of resistors that aren't in parallel or series and what to do in that kind of a case. So we start again just with this idea of the simplest circuit in the world. If we can reduce what we have to the simplest circuit in the world, which is one battery, one resistor, then we can go through and solve for the current. It's just the EMF of the battery divided by the resistance of the resistor. And so here's a case where we have two resistors in parallel. And again, what you need to have that is that you go from the top to the top and the bottom to the bottom without touching anything else. Now, a couple of things to note here is that if I call a current coming in here the equivalent current, then what happens is that current splits off into two currents. So I can write an equation here that whatever the current is coming in equals to 2. This is just our junction rule. So the current splits and travels through R1 and R2 separately. Also, since they're both connected to the top and the bottom of the battery of the EMF, the voltage drop across the resistors must be the same as the EMF of the battery. So these are two important pieces of information we can use to solve here. And what I can do is I can write it out kind of like this here. I can say, okay, well, there's the I equivalent equals I1 plus I2. And again, we're trying to find an equation that tells us the equivalent resistance in terms of these two guys here. And so I'm going to use is V equals IR equation, Ohm's law, solved for I. And so what that gets us is here is it'll be V over R1, and this will be V over R2. Here I can write the V's the same because the potential drop over everything is the same. And then here, this will be V over R equivalent. If I cancel out all the V's, because they're all the same, which is really easy to do, then I get this kind of an equation, which of course we've seen this sort of equation when we did capacitors. Be careful though, this is for resistors in parallel, so they switch these equations. They're very similar, but we switch them because of the nature of how resistors work versus capacitors work. All right, so here's an example. Why don't you give this one a try here? So what is the total current drawn from this battery? So we'll pause this and give us a try. All right, I got that the total current was 3 amps. And one way to do this is look at the equivalent resistance. And so we do 1 over 10 plus 1 over 20. And when I solve for RQ, I get 6.67. So first of all, this is less than either resistor is. Does this make sense? It does make sense. Hopefully it makes sense. Okay, because by adding 2 in parallel, you've given 2 paths for the electrons to go through. Okay, and so you've reduced the resistance by adding a new path. So there are 2 paths, more places for the current to flow. So when you're in parallel like this, the parallel equivalent will be less than either of the 2. Now you can then break this down to the simplest circuit in the world and solve for your current, and you get 3 amps. Okay, so that's the one way, probably the easiest way to do that. Another way to look at it is here. Now, since these 2 resistors, we know that the voltage of them is the voltage of the EMF, so the 20. We can say that this one has 2 amps, this one has 1 amp, and then altogether we know they have 3 amps. So we can get a little bit of insight here. We know that basically the battery is sending out 3 amps, all right? And then over here, 2 amps will go to the top part, 1 amp will go to the bottom part. And again, because of the junction rule, we know that the current, if I do a little junction, our little junction right here, we have 3 amps coming in, we have 3 amps leaving. And so everything works out in this case. So that's nice. And so here's our summarization of what we have so far for parallel and series. So like I said, these kind of ugly equations here, all right, these two have switched, but that's what they are for series. So for series, the resistance is bigger. For parallel, the resistance is less. These rules over here, though, are kind of the same. The potential difference when you're in parallel is the same. These two, when it's in series, add up to the equivalent voltage. And then here, instead of charge, we now have current. And so for parallel, the equivalent current equals the sum of the 2. And when you're in series, right, when 2 things are in series, they have to have the same current. We talked about that the other day in class. Right? So if the current comes through here, it has to go through here as well. So this is our summary sheet for everything to do with this one here. Now, one of the last things we'll be talking about in terms of circuits will be power. And so there's two ways that we sort of think about power. First of all, we talk about power supplied by the battery. And so this is here, the power supplied by the battery is the current times the EMF. Okay, and so they say sub-battery, and it's the current times the EMF. Units for power are joules per second, or what we call watts. And then we talk about the power dissipated by a resistor. So for instance, if your resistor is a light bulb, how much power is the light bulb using? How much energy is the light bulb using? And for that, we get I and then times the potential drop over the resistance. Okay? And so this is the basic way to put it. And then over here, because we have our Ohm's law, delta V equals IR, or I can plug in and get this equation in terms of where there is no voltage and when there is no current. And so depending which two of the things you know, V, I, or R, I can write the power dissipated by the resistor in different kinds of ways. And here's just a little picture of how this works, power dissipation in a resistor. So basically as the electrons are going through and bouncing off of stuff, they're adding up heat. Okay, electric field causes electrons to speed up. The energy transformation is potential to kinetic, and the collisions transfer energy to the lattice of the wire. So as the electrons are going through and rubbing against these atoms, it'll heat up. If you actually feel a wire, okay, a wire that has a current going through it will start to heat up due to this friction. All right, so kind of bringing everything together we have so far, here's an example of a circuit, and a question you might have on the test would be, what is the power delivered by this battery? So if you want to real quick give this a try, I'll give you a hint. The first thing would be to go through and find the equivalent resistance. So if you want to do that, go ahead and pause. If not, I'll work on it here in just a second. Okay, so here we have a circuit. We want to find the power delivered. So the first thing we're going to do is find the equivalent resistance of this circuit. So if you look here at this picture, the two guys, the 20 and the 30, are in parallel. So I'm going to start there. So R2 and R3 are in parallel, and so I use the uglier equation. R equivalent is 1 over 20 plus 1 over 30. And if you solve for this, you should get that it comes to be 12 ohms. So I can replace those two resistors with one that's 12 ohms. Now these two guys are just in series, and so series is the easier case. You just add them up. All right, and so the R equivalent here will just be 10 ohms plus 12 ohms, or 22 ohms. And so we have, again, our simplest circuit in the world. Now at this point, you're actually able to solve for this, everything you need. The power delivered by the battery, that's just I times the voltage of the battery. And so here, since I know it's 44 volts, okay, the current pulled by the battery is just going to be 44 volts divided by 22 ohms, or 2 amps. So 2 amps times the EMF of the battery is 88 watts. So you can actually solve for that at this point right here. Now another thing that we'll do sometimes is to go through and then, kind of like we do with capacitors, and solve for everything there is to know about all those resistors. And so let's do that too. So here we make a little chart like we used to for the capacitors with the resistance, the current, and the voltage. And so here we are, our simplest circuit in the world. So we talked about that. The resistor is 22, the EMF is 44, and so to solve for the current, we just did that a second ago, but it's 44 volts divided by 22 ohms, and you get exactly 2 amps. So now we unfold that resistor. So that resistor was both the 10 and the 12 that were in series. And so I put those onto my chart, and these were in series. So what stays the same in resistors? Current stays the same when you're in series. Remember, so when you're unfolding these resistors, one thing will always stay the same. In this case, it's the current. So the current was 2 amps. That'll be the same through both of these. And so then to find the voltage, we just use Ohm's law. So for instance, for the 12 ohm resistor, I'll write 2 amps, 12 ohms, and I get that the total volts there is 24. And if I do the same thing for the 10, I get 20. All right, so again, these things are the same, and you'll notice that the 24 and the 20, because of the loop law, have to equal the 44, right? So the voltage increase I get from the 44 as I go down the 10 and down the 12 has to be the same, and it works out to be the same, so that's a good. In our last step, we take this circuit where we are now and unfold that, the last parts, the 20 and the 30. And so we want to go through and find out everything there is to know about them as much as we can. So 20 and the 30. And here, parallel means it's the same voltage. So from those ones were unfolded from the 12 ohm resistor, right? So it's the 12 ohm resistor that became these two guys, if you remember. And so the voltage is the same. So it's the 24, which is across the 12 ohm. And then to solve for the current for the two different resistors, all right, we're going to get, that's, for instance, 24 volts divided by 20 ohms. And you get 1.2 and then 0.8 amps. And so if you look at this and break this down a little bit, the battery is sending out 2 amps. 2 amps of current go through the 10 ohm resistor. All right, and that splits up. So that splits up into 2 pieces, but notice that they add up together. So through the 20 we have 1.2 amps, and then through the 30 we have 0.8 amps. But again, those two guys add up to be the 2. And so our junction rule works there too. And you can find the voltage drop in basically any path you go around, end up back at the same part, the voltage drops are going to add up to be the same. So all of our rules here are working, which is good.